In the last class, what did we discuss? We discussed the problem of scaling an active filter for dynamic range, and the intuition is the following. The largest signal that a filter can process is limited by the supply voltage, and the smallest signal is limited by noise. All right. And we saw yesterday that the transfer function from the input to various internal nodes in the filter can have frequency response magnitudes that can be widely varying, right, whose peak responses can be widely varying, and as a consequence, one of the op amps will prematurely limit the maximum signal that the filter can process, even though the other op amps are actually quite okay, all right, and therefore it makes sense to kind of equalize the peak magnitude responses at the outputs of every op amp inside the filter, and as a result, now all the op amps will kind of saturate at for the same maximum input signal strength. Now, we also saw how we would accomplish this thing. This is a one shot procedure. First thing is to simply find the peak magnitudes at every node, and we saw how one could, we saw a recipe where you can simply scale the peak response at every node by a factor, and that is done by changing the value of the integrating capacitor or whatever is there in the feedback branch, and simultaneously scaling all the impedances that sense this node, right, the output node, by the same factor. This way, the current that was going into the branch would be the same regardless of what the voltage was. All right. So, the next thing that for the lowest limit, as we were talking about yesterday, that depends on noise, all right, and the noise is coming from all the elements inside the filter, namely the resistors add noise, it turns out, and the op amps which internally have transistors also add noise. So, the output of the filter is not merely the input signal which has been filtered, but noise of its own, and so we'll get to see how this noise behaves when we actually talk about noise, right. I mean, we could have instead of going to filters at this point, we could have talked about noise and then talked about filters later. But then a young crowd like you gets antsy when you just keep seeing theory without any application, and then right, you keep wondering why am I studying all this? All right. So the next thing we need to worry about is well, let's quickly draw filter. As we said yesterday, if we were only interested in the low pass response, it does not particularly matter whether you put the damping response, the resistor on the input side or the output side, as far as the transfer function is concerned, right. The input output transfer function is concerned, and this is Vi, this is Vo, which is a low pass transfer function. All the resistors except the damping resistor are R, for instance, and this is C, and depending on the Q, the peak transfer functions at the outputs of different op amps can be different. If the Q is very high, then it turns out that, as you will check for yourselves in one of the assignments, the peak signal at the output of this op amp A1 becomes much larger than that of A3, and then in which case you can do some dynamic range scaling and equalize the peaks. All right. The only other aspect that we have not seen so far is the following, and that is that we have assumed so far that all the op amps are ideal, right. In other words, if you apply a differential input, the output first of all becomes infinite, and not only that, not only does it become infinite, it does so infinitely fast, correct. I mean, this 1 infinity is bad enough. I mean, where are we going to get 2 infinities, right? The bandwidth is infinity and the gain is infinity. So, of course, in practice, neither the gain is infinite nor the bandwidth is infinite, all right. And it turns out, as you've probably seen in your earlier classes, that a good model to use, I mean, we don't want to go into the internals of the op amp at this point, because that will take us too far astray. If this is the differential input voltage of the op amp, and this is the output voltage of the op amp, the model for the op amp's transfer function, it turns out, is VO of S by VD of S, right, is some ADC divided by 1 plus S over omega d, and this corresponds to a 2-stage Miller compensated op amp, which is probably the most commonly used op amp. Whenever you buy a discrete op amp, a 2-stage Miller compensated op amp is the one that's used. And those of you who've done a course on transistor level circuits should be well aware how this comes about, right. That ADC, that finite gain, is simply the product of the DC gains of the individual stages, and omega d stands for the dominant, right. It turns out that typically ADC is actually very, very large. So, typically 10 power 5, 10 power 6, something like that. So, to make our life simple, we can basically say that for all practical purposes, the gain of the op amp is very, very large, and therefore, you can think of you can think of this as, so in other words, this ADC is extremely large, and this is a log scale, and this is 1, and what frequency is this is the Bode plot of magnitude plot of the gain of the op amp. At what frequency does the magnitude of the gain go to 1? ADC times omega d. So, and as you all know, the omega d is a very, very low frequency thanks to Miller compensation, and so for the useful, I mean, except at very, very, very low frequencies, you can see that there is no difference between this plot and the gain of an amplifier with this transfer function, correct. How does the transfer function of this look like? Well, that will look like this all the way here. The only difference is that, well, it keeps going to infinity at DC, and so over the useful, I mean, over a large part of the frequency range, you can see that this approximates the characteristic of the op amp, the transfer function of the op amp rather, and this is therefore this is also called the gain bandwidth product, right. Let me call that omega u by S. all right. Now, the question is, well, what happens, I mean, what is the obvious question now? If the op amp is ideal, the transfer function we would get here is would be what? 1 by or minus 1 by s square by omega naught square plus s by omega naught q plus 1, all right. And so, what is the question that we would like to ask now? Yes? Well, evidently the op amp is not what we thought. It is different from our ideal model. So, a natural question to ask would be, what does it do to the transfer function? We should expect, that there will be some change, right. For one, what comment can we, if the op amp was ideal, what comment can we make about the order of the system? Second order, right. Now, we replace the op amp with, we thought the op amp was ideal and had infinite bandwidth, but it unfortunately turns out that the model for the op amp is actually it has a frequency dependent gain given by omega u over s. So, now the question is, what is the order of this so called filter now? What is the order of the transfer function? What do you think? Well, it's every op amp is now got an additional pole. So, this would be a fifth order transfer function, right. Okay. The only hope is that if omega u tends to infinity, right. I mean, so as omega u tends to infinity, the transfer function will tend to a second order one, meaning remember that a fifth order transfer function will have 5 poles, correct. As omega u becomes very large, we will see what that large is going forward. But if omega u becomes very large, then we should expect that it reduces to, if we set omega u tending to infinity, we should expect that this fifth order transfer function should reduce to a second order one. Therefore, if you keep increasing omega u, right, 3 out of those 5 poles, right, must be tending to, should be expected to tend to infinity, because as omega u tends to infinity, this must reduce to a second order one, which is equivalent to saying 3 of the poles have gone to infinity, correct. So, if omega u, our intuition is telling us that if omega u is sufficiently large, where we still need to figure out what the meaning of that sufficiently large is, all right, we should expect to see that, well, at least in the regions of interest of our filter, namely, below omega naught and maybe a few decades above omega naught, we should expect to see that, we should be able to approximate that as a second order transfer function. You understand? Okay. So, that is the spirit in which the analysis that we see going forward has to be seen, right. It is, remember that this notion of quality factor, etc., all pertains to, Q pertains to a second order pole pair, right. So, it does not make sense to say, talk about what would be the Q of my filter, we now have a fifth order transfer function, right. But we still do talk about the Q of our filter, assuming that the omega u of the op amps is so high that in the frequency region of interest, the behavior largely looks like second order behavior, in which case you can talk about its Q. You understand? All right. So, that is one thing that I would like to clear. The next thing that I would like to talk about is, what before we go and, how do you think we would go and analyze this problem? What would we do? What do you suggest? Well, when the op amps were ideal, you know, you wrote down all the virtual ground equations, blah, 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 you can analyze the circuit, you can get your transfer function. Okay. Now, tough luck, the op amp is not ideal. So, how do we go about, finding the new transfer function? What would you do? So, well, one thing you could say is, well, I will wait for my neighbor to do the math, and then, you know, I will copy from him, right. But unfortunately, it looks like your neighbor is also, you know, assuming the same thing, right. So, you know, we are all in the same boat. So, what do you think, what is the dumbest thing that you can do? I mean, apart from waiting for your neighbor to finish, what do you think you could do? Pardon? Well, I mean, there's you know, there's no rocket science here, right? You know, you think of the op amp as omega u by s and go through the math, right? I mean, and you know, it probably is going to run into a couple of pages of algebra, right? But in the end, you will have the transfer function, all right? But that kind of analysis, you know, you can do, right? But you what have you not exploited? Well, we have not exploited the fact that, you know, typically omega u by s must be, that omega u must be, you know, is very large. You know, in some sense, right. So, you know, and we haven't exploited the fact that in the region of interest of the filter, namely omega naught and its neighborhood, right, the behavior still looks like second order if the op amp is sufficiently fast, all right. So, let us try and see if we can kind of, you know, do some kind of hack to be able to estimate what happens when the op amp has got finite gain band. All right. Now, before I go there, let me draw your attention to some background information, right. Let us say you have a second order pole pair, right, with some omega naught and q. What comment can we make about omega naught? What, I mean, in this picture, you know, what is omega naught? The radius of these two will obviously lie on a circle. This is, the magnitude of that is omega naught. And what is q? What is this? What is this distance? Apologies. You draw a vector there, the magnitude of that vector is omega naught, all right. And what is q? Remember, the quality factor q quantifies, pardon? How close the poles are to the j omega axis, right. So, what is this distance? Yes? Please do the math and let me know. Yes? It is omega naught over 2q, all right. And if q is you know, for high q, that is q much larger than 1. What comment can you make about the length, I mean, that and the hypotenuse? Pardon? It is almost equal to omega naught. So, I mean, which is why, you know, you often say that the real part actually is square root of, it is omega naught times square root of 1 minus 1 by 4q square, but for a sufficiently large q, that 1 by 4q square is so small that you know, the ordinate of that complex number the imaginary part is simply omega naught, and the real part is magnitude of the real part is omega naught over 2q. All right. So, part imaginary of the pole divided by real part the pole is nothing but, yes people, come on, this is the pole pi, this is pi star. What is the ratio of the imaginary part to the real part? For high q, the imaginary part is basically omega naught by 2q, and the real part is omega naught. So, the ratio of the the imaginary part is omega naught and the real part is omega naught by 2q, and therefore, this is 2q. All right. So, this is just something to bear in mind, right. In other words, the distance of the pole to the x axis, I mean to the y axis or the j omega axis, which is the border of instability, right, is divided by the radius of the pole, right, corresponding to the pole is basically the quality factor, right, multiplied by 2. Okay. So, in other words, you interpret the quality factor q as distance from the region of instability right. This is the should be in the denominator divided by pole. Does it make sense? This is nothing but omega naught, this is nothing but what is the distance from the pole frequency to the how far should you go? This is omega naught over 2q, right. So, the ratio of the two divided by 2 gives you the q.